welcome dear viewers. Welcome to the course Quantum Chemistry. In this module, we are discussing atomic spectra. The content of this module are atomic spectra, Bohr theory of hydrogen, the line spectrum of hydrogen, Rydberg equation, different series in the line spectrum of hydrogen, and numerical problems on calculation of wave numbers based on Rydberg equation. First of all, atomic spectra. The spectrum of electromagnetic radiation emitted or absorbed by an electron during the transition between different energy levels within an atom is known as atomic spectrum. That is, the spectra shown by electrons of the atom is termed as atomic spectrum. Or in a more simplified way, atomic spectra is the spectra shown by atoms. When an electron gets excited from one energy level to another, it either emits or absorbs light of a specific wavelength. If the emitted light is analyzed by using a spectrometer, the spectrum obtained consists of a series of sharp, well-defined lines. Such a spectrum containing well-defined lines of definite frequency is called line spectrum. For example, in the line spectrum of hydrogen, we can see the presence of enormous lines. Each line corresponds to a particular frequency. Hence, the spectrum of hydrogen is known as the line spectrum as such. The pattern of lines in the line spectrum of an element is characteristic of that element. That is, the spectrum shown by hydrogen is different from that shown by helium or nitrogen or any other element. Therefore, the line spectra have been rightly described as the fingerprint of the atoms of various elements. This implies that the atomic spectrum of one element is quite different from that of other element. The spectra produced by gaseous molecules contain distinct bands, which are families of closely spaced lines. That means molecular spectrum consists of closely spaced lines or distinct bands. That is the major difference between molecular spectrum and atomic spectrum. Molecular spectrum consists of bands that are the families of closely spaced lines. However, atomic spectrum consists of distinct lines. Now, moving on to the Bohr theory of hydrogen. The spectral features, the stability, and more or less almost all the parameters regarding the stability of hydrogen can be explained on the basis of Bohr theory. Now we are focusing the Bohr theory of hydrogen. Bohr retained the essential features of the Rutherford model of atom. Previously, the Rutherford model came into existence, and the drawbacks of the Ruther model leads it to a new model, that is Bohr theory. This implies that prior to Bohr theory, there was the Rutherford model. The Rutherford model of atom is based on a famous experiment known as alpha ray scattering experiment. And the Rutherford model fails it to explain the stability of an atom. The drawbacks of the Rutherford model is more or less compensated or rectified in the Bohr theory, especially the Bohr theory for hydrogen. However, in order to account for the stability of the atom, Niels Bohr introduced the concept of orbits in his model. In the Rutherford model, there will be no orbits. However, in Bohr model, there are orbits. Niels Bohr won the Nobel Prize for Physics in the year 1922 for his service in the investigation of the structure of atoms and the radiations emanating from them. Important postulates of Bohr theory. The major postulates are: number one, an atom consists of positively charged nucleus responsible for almost the entire mass of the atom. This means most of the mass of the atom is focused in the nucleus. Now, the position of the electrons is mentioned in second postulate. The electrons are revolve around the nucleus in certain permitted circular orbit or of definite radii. That is, electrons are revolving around the nucleus through certain circular orbits. The next one is about the angular momentum of an electron revolving in a particular orbit. The permitted orbits are those for which the angular momentum of an electron is an integral multiple of h by 2 pi. This h by 2 pi is sometimes referred as S cross or Dirac. Here in h by 2 pi, h represents the Planck's constant, the value of which we already learned, that is equal to 6.626 into 10 raised to minus 34 joule second. Now, angular momentum denoted as capital L is equal to mvr, where m represents mass of the electron, v represents the velocity, and r represents radius of the orbit. Must be an integral multiple of h by 2 pi. That is, mvr is equal to nh by 2 pi, where n is equal to 1, 2, 3, etc. Where capital L, as I already mentioned, represents the angular momentum, and this number n denotes the number of the orbit. The integer n is called principal quantum number as far as quantum mechanics point of view is concerned. This equation mvr is equal to ns by 2 pi is also known as Bohr quantization postulate or Bohr quantization of angular momentum postulate. Moving on to the fourth postulate of Bohr theory. It states that when electrons move in permitted discrete orbits, they do not radiate energy. Such orbits are called stationary state or non-radiating orbit. The fourth postulate implies that as long as the electron is staying in an orbit, there is no gain or no loss in its energy. This statement, this postulate clearly eradicates the instability of an atom which is in existence as per the Rutherford model. The last postulate of Bohr theory: the energy is radiated when an electron jumps from higher to lower orbit, and the energy is absorbed when it jumps from lower to higher orbit. This postulate implies that an electron present in a particular energy level can go to any other level by absorbing or liberating the energy difference between the orbits. To go to higher shells or orbits, the electron has to absorb energy, and for coming down, the electron has to remove its energy or liberate its energy. These all are the important postulates of Bohr theory, especially Bohr theory of hydrogen. Now, it is possible to calculate the energy of an electron in hydrogen atom or hydrogen-like system based on the postulates of Bohr theory. Niels Bohr calculate the energy of hydrogen and hydrogen-like systems by using his theory, and the resultant equation is known as the Bohr energy equation, which is shown here. En is equal to minus 1 by 4 pi epsilon 0 square multiplied with 2 pi square z square me raised to 4 divided by n square h square, where n represents number of orbit or shell, or simply the principal quantum number, which is equal to 1, 2, 3, etc. Z represents the atomic number. For hydrogen, Z is equal to 1. M represents mass of electron, that is equal to 9.1 into 10 raised to minus 31 kilogram. E represents the charge of an electron, that is 1.602 into 10 raised to minus 19 coulombs. H is Planck's constant, its value is 6.626 into 10 raised to minus 34 joule second. The parameter 4 pi epsilon 0 represents the permittivity factor, corresponds to the medium in which the atom is situated. On substituting the knowing values in this equation, for hydrogen atom where Z is equal to 1, we will get a simplified expression. The simplified expression for energy for hydrogen atom is En equal to minus 13.6 electron volt divided by n square, where n is equal to 1, 2, 3, etc. In these two equations, you noticed about the negative value of electronic energy. This came from a simple concept. Prior to the formation of atom, electron and the nucleus were at infinitely separated distance. That means there is no interaction between nucleus and the electron. So their energy can be practically taken as zero prior to the formation of the atom. During the formation of the atom, the nucleus and the electron approach together to get to the stable atom. As a result of the Coulombic force of attraction between positively charged nucleus and negatively charged electron, there occur some strong attractive force, which leads to diminishing of energy, decrease in energy, and hence energy of the electron is also decreased, but decreased from zero, because electron previously at infinity having a zero energy. It is now reduced from zero, so we get a negative value of electronic energy. So for hydrogen with atomic number 1, the simplified energy expression is En is equal to minus 13.6 electron volt divided by n square, where n is 1, 2, 3, etc. Now, we are moving on to the line spectrum of hydrogen. When gaseous hydrogen enclosed in a glass tube is subjected to high potential difference, the gas emits a brilliant reddish purple light. If this light is viewed through an instrument called spectroscope, we can see the presence of 4 major lines in the visible region of the hydrogen. These 4, there are so many other lines also occur in other regions, but 4 prominent lines are present in the visible region. The wavelengths of the 4 major lines that appeared in the visible region of the hydrogen spectrum are denoted as H alpha with a wavelength of 656.28 nanometer, that is the red line, H beta with wavelength 496.13 nanometer, which is a green line, H gamma having wavelength 434.05 nanometer, which is a blue line, and the last prominating line is denoted as H delta with a wavelength of 410.17 nanometer, that is violet emission. It should be noted that the lines that appear in the visible region of the line spectrum of hydrogen is named as a particular series. That series is called the Balmer series. There are other series also. We can move on to the details of all the series of the emission spectrum of hydrogen in the coming slides. This is the pictorial representation of emission spectrum of hydrogen, where you can see the presence of 4 distinct lines. Red emission corresponds to H alpha, green emission corresponds to H beta, blue emission corresponds to H gamma, and finally violet emission corresponds to H delta, all in the Balmer series, especially in the visible region. Now, we have to calculate the wave number of spectral lines that appeared in the line spectrum of hydrogen. For that, we require some equations. According to Bohr, the spectrum arises when the electron in the initial higher stationary orbit of principal quantum number Ni jumps into final lower stationary orbit of principal quantum number N final. The difference in energy is emitted as photons of frequency nu. This implies that electrons are now present in Ni level, that is initial orbit. They jump down to N final level. As a result, some amount of energy will be liberated. This appears as photons of frequency nu, that is marked as lines in the line spectrum of hydrogen. Thus, for the hydrogen atom, the frequency can be calculated by using this expression. That is, for the transfer of electrons from a higher level to low level, we can calculate the frequency during this equation. That is, nu is equal to 1 by 4 pi epsilon 0 square 2 pi square m e raised to 4 divided by s cube into 1 by n f square minus 1 by n I square, where n f represents the final state and n I represents the initial state. We know that this equation is directly derived from Bohr energy equation that we already learned. Nu is the frequency, which can be substituted by C by lambda, because nu is equal to C by lambda. Therefore, C by lambda again equal to 1 by 4 pi epsilon 0 square multiplied with 2 pi square m e raised to 4 by s cube again into 1 by n f square minus 1 by n I square. Here kindly note that Ni and Nf represents the initial and final number of the orbit. Thus, the wave number can also be calculated from the above equation. Nu bar is the wavelength. Nu bar is equal to 1 by lambda. That can be marked as nu bar or 1 by lambda equal to Rh into 1 by Nf square minus 1 by Ni square. Here, Rh is a numerical constant which is known as Rydberg constant for the hydrogen atom, and the Rydberg constant here is Rh equal to 1 by 4 pi epsilon 0 square 2 pi square m e raised to 4 divided by s cube c, where c represents the velocity of the light. The wave number of any line of the hydrogen spectrum can be calculated by using this equation. This equation, which incorporate a Rydberg constant, is known as the Rydberg equation. This implies that we can calculate the wave number of any line in any series of the hydrogen spectrum can be calculated using this equation. The equation is once again nu bar equal to 1 by lambda, that's equal to Rh into 1 by Nf square minus 1 by Ni square. Here, the numerical value of Rydberg constant Rh is given. Rh is equal to 109678 centimeter inverse, or 1.09678 into 10 raised to 7 meter inverse. The first value is in CGS system, hence the unit is centimeter inverse. The second value is in SI system and the unit is meter inverse. These two values are very, very important as far as the calculation based on Rydberg equation is concerned. Now, we can move on to different series that may appear in the hydrogen spectrum. I already mentioned the fact that there are enormous lines in the emission spectrum of hydrogen. We can classify these lines into different series based on their appearance in different regions of the electromagnetic spectrum. And we are now discussing about different such series. The first series is Lyman series. In this series, the spectral line corresponds to the transition of the electron from some higher energy to the lower energy state corresponding to n final equal to 1. That is for the Lyman series. In the Rydberg equation, we can put nf is equal to 1 and ni may be any value higher than 1. These lines are found in the ultraviolet region of the electromagnetic spectrum. Moving on to the second series that we already mentioned, that is nothing but the Balmer series. The spectral lines corresponds to transition of the electrons from some higher energy to the lower energy state corresponding to n final equal to 2. That is, for Balmer series, we can calculate wave number as nu bar equal to Rh into 1 by 2 square minus 1 by ni square. This is because for the Balmer series, the value of n final is fixed, that is equal to 2. And n initial is any number higher than 2. These lines, as I already mentioned, is appears in the visible region of the electromagnetic spectrum. Now another series is called the Paschen series, for which n final is equal to 3 and n initial is higher than 3 and nu bar equal to Rh into 1 by 3 square minus 1 by ni square, where ni is always greater than 1. The minimum value of ni is 3 plus 1, that is equal to 4. These lines are found in the IR region, infrared region of the electromagnetic spectrum, preferably in the near infrared region. The fourth series in the hydrogen spectrum is named as bracket series. And for the bracket series, the n final is equal to 4 and n initial is 5, 6, 7, etc. That is, n initial is always greater than n final. These lines are found in the infrared region, preferably in the middle infrared region of the electromagnetic spectrum. Now moving on to the fifth series, that is called the Fun series. For the Fun series, the value of n final is fixed as 5 and n initial is 6, 7, 8, etc., which is always greater than n final. The Rydberg equation is nu bar is equal to Rh into 1 by 5 square minus 1 by ni square. It should be noted that these lines are found in the far infrared region of the electromagnetic spectrum. Since the infrared region is a broad region, we can divide it into 3 sub-regions: near infrared, middle infrared and far infrared. This Fun series appears in the far infrared region of the electromagnetic spectrum. Moving on to last series of the hydrogen spectrum, that is the Humphrey series. It should be noted that the Humphrey series is the recently discovered series of the hydrogen spectrum, for which nf is equal to 6 and we can write the Rydberg equation nu bar equal to Rh into 1 by 6 square minus 1 by ni square, where ni, as I already mentioned, is always higher than nf. Here ni is equal to 6, 7, 8, 9, etc. 7, 8, 9, etc. It should be noted that these lines, the lines of the Humphrey series, also found in the far infrared region of the electromagnetic spectrum. Now, all the series are depicted in a pictorial representation here. These are various levels denoted as n is equal to 1, 2, 3, etc., etc. are higher levels. The ground level is n is equal to 1. All the emissions that happened from higher levels to initial level, to the final level, n summum 1 leads to the Balmer series. If the final level, n final is 2, that leads to Balmer series. That is, Balmer series obtained by the transitions originate from higher levels, higher than 2 to the second level. If the transition is to the third level, that leads to Paschen series. If the transition originates from higher levels and ends in the fourth level, we will get to the bracket series. Fifth level and the sixth level leads to Fund and Humphrey series as shown in this picture. Now, we can have some numerical problems to calculate the wave number of spectral lines using Rydberg equation. We are moving on to the first problem. The first problem is calculate the shortest and longest wavelength of Lyman series in the hydrogen spectrum. And we have to use suitable equation for the calculation of that. We have to get the brackets, the boundaries, the shortest wavelength and longest wavelength of the Lyman series. For that, we have to move strategically. And the Rydberg equation used for this purpose is like this: nu bar or wave number equal to 1 by lambda equal to RH into 1 by n final square minus 1 by n initial square. And the problem is about Lyman series. I already mentioned the fact that for Lyman series, value of n final is fixed as 1. Now, we have to fix the value of n initial to get the shortest wavelength and the longest wavelength. So, to get the shortest and longest wavelength, you can select two values for Ni. If Ni is 2, it should be noted that Ni must be higher than n final. Therefore, the possible values of Ni are 2, 3, 4, etc. and finally the value may be infinity. So, for two limiting conditions, Ni has a minimum value of 2 and a maximum value of infinity. By selecting either 2 or infinity as the value of Ni, we will get two different brackets of wavelength, two different wavelength values, one being the shortest and one being the longest. In order to get the shortest wavelength, we have to use Ni as infinity. And to get the longest wavelength, take Ni as its minimum number. That is, Ni should be 2. By putting the value of Ni as infinity and Nf as 1, by using this equation, we can calculate the shortest wavelength. The calculation is like this: 1 by lambda is equal to RH into 1 by 1 square minus 1 by infinity square. 1 by infinity is equal to 0. Therefore, 1 by lambda is equal to RH as such, or lambda is equal to 1 by RH. You know the value of RH, that is 1 by 1.0967 into 10 raised to 7. On rearranging this, we will get a value, the shortest wavelength, 912 angstrom. 912 angstrom. This is the shortest wavelength for the Lyman series. Proceeding in an analogous fashion, by using Ni is equal to 2, we will get the longest wavelength. For this, 1 by lambda is equal to RH multiplied by 1 by 1 n final square, that is 1 by 1 square, minus 1 by 2 square, that is equal to RH multiplied by 1 minus 1 by 4, that is 3RH by 4. This is equal to 1 by lambda. This is equal to 1 by lambda. Hence, lambda is equal to 4 by 3RH. On substituting the value of RH equal to 1.0967 into 10 raised to 7, we will get the longest wavelength, and the longest wavelength is 1215 angstrom. Hence, by using the Rydberg equation, we will get shortest wavelength of the Lyman series as 912 angstrom, and the longest wavelength is 1215 angstrom. All other lines in the Lyman series are in between these two ends. So, 912 and 1215 angstrom are the wavelength limits of the Lyman series of the emission spectrum of hydrogen. Moving on to another problem, that is, we are going to find out the longest wavelength of Balmer series. For Balmer series, the value of n final is fixed, that is equal to 2, and n initial may be 3, 4, 5, 6, etc. up to infinity. I already mentioned, for longest wavelength, the value of Ni should be minimum. That is, for longest wavelength, I have to take Ni equal to 3. And substituting the value of Nf and Ni in the Rydberg equation, that is 1 by lambda is equal to RH into 1 by n final square minus 1 by n initial square, that is equal to RH multiplied by 1 by 2 square minus 1 by 3 square, that is equal to RH multiplied by 1 by 4 minus 1 by 9, that is again equal to 5 by 36. RH is in the numerator. This is 1 by lambda. Therefore, value of lambda is equal to, taking reciprocal, that is 36 divided by 5 into RH. We know the value of RH equal to 1.0967 into 10 raised to 7 meter inverse. This is the value of RH. Substituting the value of RH, we will get the value of lambda, and the value of lambda obtained will be the longest wavelength, the limit of the Balmer series. On proper substitution, we will get the final value nearly 6600 angstrom, approximately 6600 angstrom. by putting Ni is equal to infinity, we can also get the value of the shortest wavelength. And from the value of the shortest wavelength and the longest wavelength, it can be concluded that all the lines that belongs to Balmer series appear in the visible region of the electromagnetic spectrum. Thus, by this discussion, we have completed hydrogen spectrum, Bohr theory, atomic spectrum, and several calculations based on Rydberg equation. That's all about the present module. Wish you a happy learning experience. Thank you.